And so today we have Charles Walker back to talk about distributive laws and pseudo-distributive laws and decagons. So you can start when you're ready, Charles.
Thank you, John. Right, so I'll start off just by giving some background knowledge. So the definition of monads in the usual monoidal form, and also this extensive form, which is in Walter's PhD thesis, was also in a paper of Menez. I'll remind you about distributive laws of monads and Beck's theorem for distributive laws. Right, then I'll say a bit about, say, pseudomonads in monoidal form, and also the definition in extensive form. And then what is known about pseudo-distributive laws of pseudomonads, at least until now. And then I'll talk a bit about distributive laws of monads in extensive form. And what I'm going to do is basically extend to the Kleisli category extensively. But by this, I mean, so we want the monad on the Kleisli category to be in an extensive form as well. Right, and as you'll see later on, this is how we get these decagon conditions. Right, and then I'll tell you the 5 coherence axioms for a pseudo-distributive law. And then I'll explain, so the three redundant coherence axioms and where they come from. Right, and so then lastly, at the end, I'll talk a bit about, so minimal definitions. When I say minimal, I mean, so like the total number of sides the shapes have and the total number of coherence axioms. Right, we'll do this for, say, distributive laws and pseudo-distributive laws. And then at the end, I'll just mention some future work. So there's a bunch of possible future directions you could go with this. Right, so a monad in monoidal form is just a functor T on a category C, from C to C, a unit 1 to T, which is natural transformation, and the multiplication T to T, such that these two triangles and the square commute. So there's the more interesting definition due to Walters and Menez, which is this extensive form definition. Right, so a monad in extensive form just can be an assignation on objects. So given any object X, we have a new object Tx, which I'll call Tx. And also for any object in our category, we have to give a unit map from X to Tx. And I should point out here, I'm not assuming that this is a natural transformation. We're just giving the data, right? And then for each map F from X to Ty, we have to give a map Tx to Ty, which I'm going to call the extension of F. Right, and then this data is meant to satisfy 3 axioms. So first of all, so these triangles are meant to commute, right? So the extension restricted along the unit should just be the F that we started with. We also have some axiom that says the extension of the unit should just be the identity. And finally, we have some axiom which I usually think of as saying that extensions are preserved by other extensions. Right, so if we have an F composed with the extension of G, and we take the extension of that, that's the same thing as composing the extension of F with the extension of G. Right, and you can go back and forth between, so the extensive definition and the monoidal definition. Right, so if we're given an F from X to Ty, we can define our extension of F as just this map T of F composed with this multiplication at Y. right? And if you're going the other way, if you're given a map, say t squared to t, right, so conversely, this multiplication map is just recovered by extending the identity, right? And the unit constraints are the same in both, are the same data in both the extensive and the monoidal form. Right, so if you do this, this gives you a bijection between monads in the monoidal form and the extensive form. This is in so Walter's PhD thesis and Menezes' paper. So remind you about the usual definition of a distributive law. Right, so a distributive law between monads, say TUM, and they're going to call the other monad P eta mu. It's just a natural transformation TP to PT, rendering commutative these 4 diagrams, right? So 2 triangles and 2 pentagons. The most basic example would be where T is the monad for monoids and P is the monad for abelian groups. Then the usual distributive law of multiplication and addition, which is this map from TP to PT, is just taking products of sums to sums of products. Right, so we take a product of sum to a sum of products like this. And you can verify that this satisfies all the coherence axioms listed here. Right, and in this case, you'll get a composite monad, and the composite monad will be the monad for rings. Right, so it's a theorem of Beck. So given that monads TUM and P, say eta mu, following our ring bijection. So distributive laws from TP to PT, and liftings of the monad P to the category of T algebras, that's denoted alg T, and extensions of the monad T to the Kleisli category of P, call it the Kleisli of P, and monad structures on the composite, which are suitably compatible with the original monads T and P. Right, so there's some middle unitary law that has to hold, and a couple of things have to be monad morphisms. But for the purpose of this talk, I'm only going to be looking at extensions to the Kleisli category. Right, so I should remind you what the Kleisli category is, since we'll be using it. So if you're given a monad P eta mu, then the Kleisli category of our monad P is denoted, so the Kleisli of P, it's going to be the category of the same objects as those of C. And the Kleisli morphism, I'm going to write it as a twiddly arrow from X to Y. It's just going to be a morphism from X to Py in our original category. And composition in our Kleisli category. So if we're given a Kleisli morphism from X to Y and a Kleisli morphism from Y to Z, i.e. a morphism from X to Py and a morphism from Y to Pz, then the composite is going to be given by this F followed by P of G followed by the multiplication of P. Right, and this is a Kleisli arrow from X into Z. Maybe I'll just mention here that you could write this composite, say PG mu Z as G to the P, right, the extension of G. Right, so when you use the extensive form, it becomes a bit easier to talk about composition in the Kleisli category. So that's why sometimes it's called the Kleisli presentation of a monad, Kleisli triple, so on. Right, so if we're given monads, say TUM, P eta mu on a category, so what does it mean to extend to the Kleisli category? Well, an extension of a monad TUM to the Kleisli is going to be a monad, let's call it T twiddle, U twiddle, M twiddle, on the Kleisli of P, such that this diagram commutes, written, say, T twiddle F equals FT, and the monad data should be compatible as well, right? So the U twiddle and the M twiddle. And so this just means that U twiddle F is FU and M twiddle F is FM. Right, well, these are some whiskerings. Right, so if you're given a lambda, you can define T twiddle by sending a map F from X to PY to this map TX to PTY. So I just remark that, so in the Kleisli, this is an arrow from X to Y, right? And in the Kleisli, this is an arrow from TX to TY. Right, so we're just defining what T twiddle does. So we send a morphism F from X to PY to this constant F followed by a lambda of Y. And if you work out what you require to ensure that this given lambda gives us an extension to the Kleisli using the usual monoidal form definitions of monads, then you'll naturally arrive at Beck's 4 coherence axioms for distributive laws. Right, now the interesting thing is, if you work out what's required to ensure that this lambda gives an extension to the Kleisli with this extended monad in extensive form, then you'll arrive at a different set of axioms. And maybe you can already see this. That's because the definition of a monad in extensive form has literally just 3 things to check, right? So it's those 3 axioms. Whereas in monoidal form, it looks like 3 axioms, but actually it's 4, because you have naturality conditions and functoriality. Right, so one of the simplifications that happens in CAT when monads are presented in extensive form is you can avoid these functoriality and naturality conditions. And so that's why we will actually just get 3 coherence axioms for distributive laws when we're doing it in this extensive form. All right, so I'll remind you about pseudomonads. So it will be the 2-dimensional version of monad that I'm using. I'll talk more about this later on. Right, so a pseudomonad on a 2 category, which is going to be a pseudo-functor, say from C to C. Now a pseudo-natural transformation U from 1 to T, and the pseudo-natural transformation M from T squared to T, along with 3 modifications, all invertible. And these should satisfy 2 coherence axioms. Right, so we have some coherence diagram like this, which involves the 2 different units and our associator, if you like. And you also have this axiom, which might look a bit scary at first. What's going on here is that this is just some version of McLean's pentagon on the associators. Right, so we have these 5 gammas here. Right, and so this is the other axiom, if you like, for a monoidal category of the triangle equation with the 2 units and the associator. Right, and this happens because monoidal category is a pseudo-monoid in CAT, and the pseudo-monad will be a pseudo-monoid in the 2 category of endo-pseudo-functors, or really a grey monoid. Yeah. Now it was shown by Kelly that if you have these 2 axioms, then we get 3 redundant axioms that will follow from this. Right, so we have an axiom involving just the same unit, the dual thing here, and there's also this really simple axiom just involving the 2 different units. Right, and so the interesting thing is that actually this is going on inside the coherence axioms for pseudo-distributive laws. Right. It's not entirely obvious at first because the coherence axioms for a pseudo-distributive law look a bit different, right? Except for one of them, right? There is a simple axiom that's just some simple axiom involving 2 different units. And that axiom actually does directly appear. But somehow it only becomes clear that this is going on when you use decagons instead of pentagons, which I'll talk a bit about later on. All right, so what's the definition of a pseudomonad in extensive form? All right, so this was first given in paper of Marmolejo, but I'm going to use the definition given in this paper in terms of relative pseudomonads, just with the relative part taken to be the identity. So I made some simplifications. All right, so a pseudomonad in extensive form is going to be an assignation on objects, x to tx. So for each x, we give a map from x to tx, as like before. And now for each xy, we have to give a functor. Same thing, the hom categories x ty to tx ty. All right, so in one dimension, these were just functions. Here they'll be functors. Right, and last time we had three conditions that they had to satisfy, but now those conditions will only hold up to an isomorphism. Right, so the triangle from earlier for an EF now is only going to commute up to some isomorphism, which we're going to call 5F. And the extension of a unit is going to be isomorphic to an identity. Right, so we'll call this theta of x for the unit at x. And the extensions are only going to be preserved by other extensions up to some isomorphism, which I'm going to call delta. Right, and then this will satisfy two coherence conditions as earlier. Right, so we have the axiom with the two different units and the associator. Right, so this coherence condition. So for any f x t y, this diagram commutes. And then you also have some version of Maclane's pentagon axiom, right? So same thing, same sort of thing as before. And then in much the same way as earlier, we also have these three redundant coherence axioms that follow from what Kelly did. Right, so the simple axiom involving the two units, and then those other two axioms. Right, so maybe now I'll say a bit about the history of pseudo-distributive laws. Right, so like why I use pseudo-distributive laws? Well, actually, even if you just start off with natural examples of two monads, it's often the case that you have to use pseudo-distributive laws. So an example of this is where T is the two monad for small symmetric monoidal categories, and say take T to be the two monad for small categories with finite products. Then there's no natural two distributive law, so no strict distributive law, TP to PT. Basically, the problem is that one of the pentagons doesn't commute strictly, but it does commute up to some natural isomorphism. Right, and so we have to allow these diagrams to only commute up to some invertible modifications. And these modifications have to satisfy some coherence conditions. But actually, these coherence conditions on the modifications are the complicated part here. So there's a history of all these coherence axioms on these four modifications. So the first to consider this was Kelly, where he considered the case where, say, both triangles commuted strictly and one pentagon commuted strictly. Right, and he arrived at 5 coherence axioms in this case, with these semi-strict distributive laws. Right, of course, Kelly was motivated by these examples where only one pentagon is causing problems, right? Then Marmolejo considered the general case with the 4 modifications, and he found 9 coherence axioms for these. Right, and then in Tanaka's thesis, he introduced an extra 10th coherence axiom. Then after this, so Marmolejo and Wood showed that both Tanaka's extra axiom, in addition to one of the original 9 axioms that Marmolejo had, are redundant. That's showing that 8 coherence axioms suffice. And so the way they showed this was that they showed that a pseudomonad morphism had 2 coherence axioms, not 3. Right, so the original definition of a pseudomonad morphism had 2 unitality axioms and 1 associativity, but it turns out that one of the unitality axioms was redundant. And actually, there's an easy way to see that if you know it for algebras, because if you know that the definition of a pseudo algebra, you just have a single unitality axiom and some associativity condition, and then another unitality axiom follows from that. And that's because a pseudomonad morphism can be seen as a certain pseudo algebra, right? So the same thing happens with those coherence axioms. Right, so today I'll show that actually just 5 coherence axioms is enough to define a pseudo-distributive law. Right, so the version of Beck's theorem for pseudo-distributive laws has given pseudomonads TUM and P and E sub nu. I'm going to suppress the modifications that comprise the pseudomonads because we don't care about them so much. And the following are equivalent. So pseudo-distributive laws, liftings of the pseudomonad to the 2 category of pseudo-algebras, extensions of the pseudomonad to the Kleisli bi-category, and pseudomonad structures on the composite, which have to satisfy a bunch of compatibility conditions with the original pseudomonads T and P. And again, we'll only be interested in extensions to the Kleisli bi-category. Right, so let's suppose that we're given some monads TUM and P to U. So let's work out what it means to extend a T twiddle U to extend a TUM to the Kleisli category of P, where our extension T twiddle is defined in extensive form. Right, of course, you can just ask for a monad T twiddle, which is like T in objects, has this unit constraints given by this formula, and satisfies the obvious condition with the extension operators. But that's not what I mean here. What I mean here is, given a lambda, what conditions do I need to get a extension to the Kleisli category defined in extensive form? Right, so if we're given our lambda, we need to define our monad in extensive form. So clearly T twiddle will be the same as T on objects. We define our unit, which will be a squiggly arrow or a Kleisli arrow from X to Tx, i.e. an arrow from X to PTX as this composite. And for a general F, for Kleisli arrow from X to Ty, i.e. an actual arrow from X into PTY, we define our extension of F by this formula. Right, so this will be our arrow from Tx to Ty in the Kleisli. Right, so we're meant to check some. So in one dimension, we're meant to check that these diagrams commute. So what does this condition actually tell us? Well, it says that for any F, which is this composite along the top, that should be equal to this composite of these 2 things here. Now, if you work out what UX twiddle is, and this F to the T twiddle is, and then you use the formula for composition in the Kleisli category, you'll end up with this composite going along the bottom. And so you need these things to be equal. And so you end up with, say, this coherence diagram. Right, and so what condition do you need to make this work? Well, the only thing you need is this triangle with UP lambda and PU. So what we just mentioned, so in one dimension, you can think of, so just this omega 1 and this phi is just a name for some condition. But in the 2-dimensional case later on, these are going to be modifications. Right, do the same sort of thing, asking that the extension of the unit should be the identity. right? So the extension of the unit here will give us this composite. And actually, this is the identity, right? The identity in the Kleisli is the unit of the monad. So we get this coherence condition here. And then in order to make this diagram commute, we just need this axiom with T eta lambda being e to T, right? So the other triangle axiom. But the interesting thing is this one. So this condition about extensions being preserved by other extensions. Right, so the coherence condition you need for this is that, so this top path should be equal to this bottom path. And so what axiom do you need to make this work? Well, you just need this decagon to commute. Right, so we naturally arrive at this following definition of a distributive law, which we'll call a distributive law in extensive form. Should be a natural transformation Tp to Pt, rendering commutative these three diagrams. Right, so there's two triangles and the decagon. Right, this is equivalent to the usual definition. And the slightly surprising thing is that this also works for, say, mixed distributive laws. I mean, you might think of this decagon as kind of a restriction of the associator of the composite monad along one of the units, which would be one way to get it. But in the mixed case, you don't even have a composite monad. So maybe slightly surprising that this actually still works here. So again, in the mixed case, we have two triangles and some decagon axiom. And this is equivalent to the usual definition. Actually, in the mixed case, it's a bit more complicated somehow. The decagons still show up, but they show up a bit less nicely. Right, so what about pseudo-distributive laws? Right, so now I'll tell you the 5 coherence axioms of a pseudo-distributive law, using the usual definition. Right, so a pseudo-distributive law, say in monoidal form, so in the usual form, it's going to be a pseudo-natural transformation, Tp to Pt, and it's 4 invertible modifications, like this, satisfying this following 5 coherence axioms. Right, so you have some axiom that says the restriction of the pentagon along the unit should be the identity. You might want the unitality axioms. Another axiom says the other pentagon restricted along the other unit should give us the identity. And an axiom that says the pentagon omega-3 satisfies associativity, which looks like this. An axiom that says pentagon omega-4 satisfies associativity. And you have this slightly complicated looking axiom, which says that this pasting diagram of these pentagons, omega-4 and omega-3, equal to this pasting of omega-3 and omega-4. Right, so you might think of this as a little bit like an interchange, because you have an omega-3 on the top, omega-4 on the bottom. Here you have the omega-4 on the top and the omega-3s on the bottom. Right, and so in a sense, this is the best that you could possibly hope for, in that a pseudo-distributive law is the same as a pseudomonad morphism, the pseudomonad morphism, and you only need one coherence axiom to ensure that the pseudomonad morphism and the pseudomonad morphism are compatible. Right, so of course I'll prove this a bit later on. So now I'll give a definition of a pseudo-distributive law. So in the extensive form, so using decagons. Right, so this would be a pseudo-natural transformation, say Tp to Pt, and 3 invertible modifications. So one in each of the 2 triangles, and one inside the decagon, which I'll call capital omega. Might look a bit strange, but this is what you need to reduce the coherence axioms for pseudo-distributive laws. Right, and actually, the nice thing that happens here is now you're only going to need 2 coherence axioms, right? Because the definition of a pseudomonad in extensive form has just those two coherence axioms. Right, so we have some coherence axiom that says that the decagon restricted along both units should give us the identity. Right, and then we have the slightly scary looking axiom that's Maclane's pentagon axiom somehow. Right, so we have it as capital omega pasted with p omega. Should be this pasting of omega pt and tp omega. Right. So in order to prove that all these definitions of pseudo-distributive laws are correct, we need to prove the following theorem. So that the following equivalents. So pseudo-distributive laws in monoidal form, so using the 5 coherence axioms. So in extensive forms, the definition I just mentioned, and the extensions of TUM to the Kleisli bicategory with P is a U, mu. So the first thing you'll check is that, so for a given lambda, the data, so omega 1, omega 2, omega 3, omega 4, so the 2 triangles and the 2 pentagons with the 2 unit axioms, within bijection with the data, so omega 1, omega 2, and capital omega, so the decagon, with the unit axiom on the decagon. And so if you're given the pentagons, you can construct the decagon just by this pasting diagram of the 2 pentagons. Right, and we can also go, so the other way. Right, so if you're given the decagon, how do you get the pentagon back? Well, it might be a bit scary at first, let me explain. So if you want to recover a pentagon, say omega 4, you start off with the TP squared, because that's what it starts with. And then you just insert the units that you need until you reach the decagon. Right, and then it's just a matter of simplifying the diagram. And when you do that, you'll end up with whatever axiom you want. Right, and so we'll recover this pentagon omega 4 as this pasting diagram. And the same sort of thing for the other pentagon omega 3. Right, so you start with t squared p, insert the units that you need until you reach the decagon, and then simplify. Actually, it's not hard to check that this is a bijection. I mean, you can already sort of see that these the unit axiom on the decagon is quite similar to both of these 2 unit axioms on the pentagons. And actually, this shows that these definitions are equivalent because, so this scary looking axiom involving the plane's pentagon, axiom D2 I was calling it, that involves only decagons, but the decagons are constructed from only pentagons. And so that actually follows from the pentagon only coherence axioms for pseudo-distributive laws, which are exactly those 3 coherence axioms. And you could go the other way as well and recover these axioms by restricting this scary looking diagram D2 along the units of the monads. Right, so you just need to check that you actually get a pseudomonad on the Kleisli bicategory from this. But I mean, that's clear because these axioms, say D1 and D2 with the decagon form, that's exactly what you need to define a pseudomonad using the extensive definition of a pseudomonad. Right, so the axiom was just the 2 units in the associator and Maclane's pentagon. Right, so now I'll say a bit about the redundant coherence axioms, so where they come from. Right, so let's first recall that for any pseudomonad in extensive form, we naturally get these 3 redundant coherence axioms. Right, so this first axiom tells us that a phi, which if you remember from the start, was constructed from some pasting of what I was calling omega 1, followed by a theta, which was constructed by some pasting from an omega 2. Right, so this condition that this is an identity Well, this is exactly this coherence axiom for a pseudo-distributive law. Right, this redundant axiom. What about this one? So where does this axiom come from? Well, the way you would prove this is, so the first thing would be to sub in the formula for this omega-3 in terms of the decagon from earlier, right? So, I mean, this looks a bit scary, but the point is omega-3 was just some pasting of the decagon capital omega with the unit omega-2. Right, so if you sub that in, then you can apply this redundant axiom to turn this omega-2 and the decagon capital omega into just a single omega-2. Right, and so when you do that, you'll end up with some pasting diagram just containing two omega-2s, right? And that's exactly this diagram. Right, so that's how you recover this redundant coherence axiom. Right, and of course, the other one is just going to be the dual process of this. So you sub in the formula for this pentagon omega-4 in terms of the decagon, and then use the other redundant coherence axiom for a pseudomonad presented in extensive form. Right, so maybe I'll say a little bit about the minimal definitions now. Right, so what's the point of distributive laws? So I'll say, well, to give a minimal description of, so the data and the coherence axioms that you need to compose monads or extend to the Kleisli or lift to the algebras and so on, right? So it raises the question, what's the minimal definition? And the surprising thing is that actually this depends on your definition of minimal. Right, so there's two definitions of minimal you might use. One would be to break down into the irreducible lowest order components, right? Or the other definition of minimal you might use is the total number of sides all the shapes have and the number of coherence axioms. Right, so in this sense of breaking into lowest order components, Beck's definition of distributive law is minimal. But in this sense, it's not minimal. Right, in the sense of number of sides and coherence axioms. Right, so Beck's definition has, say, 16 sides, so 2 pentagons and 2 triangles, and 4 coherence axioms. Right, and the minimal definition, or likely minimal, has 12 non-identity sides and 3 coherence axioms. Right, so how do we get this minimal definition? Well, what you do is you combine all this earlier stuff, decagon stuff, with this following result of Marmolejo, Wood, and Roseborough. Right, so this is in their paper called The Basic Distributive Law. So they show that, say, distributive laws of monads, they're in bijection with, say, T algebras, alpha from TPT to PT, rendering commutative these 3 coherence diagrams. Right, so let me just explain these diagrams. Right, so when you do a change of variables for replacing a lambda with an alpha, then 2 of the unit axioms, so 2 of the triangles become transformed. So you get one of the unit axioms, tries to put in the algebra definition here, and this square is the other unit axiom. Then this is sort of a transformed version of one of the pentagons, and the multiplication algebra axiom here is the kind of other transformed version of the pentagon. And then you have this axiom, which just makes sure that this change of variables going between lambda and alpha is actually a bijection. Right. And so if we use decagon stuff, we get this following. Right, so distributive laws in the sense of Beck, so lambda from PT to PT, they're in bijection with natural transformations alpha from TPT to PT, rendering commutative these 3 diagrams, right? The triangle, the square, and the hexagon. Right, so what's going on here? Right, so what's going on here is that this hexagon is and it's secretly the decagon from earlier. Right, so something nice that happens is that the decagon collapses into the hexagon when you do this change of variables. The other nice thing that happens is this extra axiom you need to make the change of variables of bijection turns out to be redundant in this setting, which is maybe slightly surprising. Right, so as for proving this, it's just a matter of showing that, so this set of 5 coherence axioms, right? So these 3 and these 2 algebra axioms are equivalent to my set of 3 coherence axioms. And so for this 5 axioms implies 3 different direction, that's just a matter of checking this one, which just comes from, so this pasting diagram. And conversely, just given the 3 axioms, so these 3, you can recover the multiplicative algebra axiom as just this pasting, as this diagram, using the square and hexagon axioms. You can recover this sort of, well, I call it a homomorphism axiom, this one that gives us a bijection between the change of variables. Because if you write things on the other side, then it looks like a homomorphism axiom. Right, so this just follows from, so using the square axiom twice and the hexagon. And this transformed looking version of the pentagon they had just follows from restricting the hexagon I had along one of the units. Right, so that's the proof of that theorem. And so let me just mention that there's also the dual version of this, but based on sort of op algebras instead of algebras. And so instead of an alpha going from TPT to PT, here you would use a morphism from PTP to PT. Right, and this would be the sort of P embedding structure or the P admissibility structure on the map TY. People that know about that sort of thing. Right, and I think that this dual version sort of naturally shows up when you lift to the category of algebras kind of extensively instead of doing the Kleisli stuff. Right, I can do the same sort of thing for pseudo-distributive laws to get the minimal definition of a pseudo-distributive law. Right, so pseudo-distributive laws are in equivalence with pseudo-natural transformations, say TPT to PT, equipped with 3 invertible modifications, right? So one inside the triangle, one inside the square, and one inside the hexagon. And then these 3 modifications should satisfy the 2 coherence axioms. All right, so this, I'm calling it a capital Xi because it was secretly the decagon from earlier. So capital Xi pasted with the 2 units should give us the identity. And then you have the McLean's pentagon version of this. So some pasting of P, capital Xi and Xi. We give this pasting of Xi, Xi PT and TP Xi. Right, and as for proving this, it's just a matter of proving that this, so earlier definition involving the decagons, the assignation of that into this, which is actually pretty easy to see is well defined, is an equivalence. And that's basically just a matter of checking a whole bunch of coherence diagrams. Right, and the fact that this diagram pseudo-commutes, which means that you'll have a sort of this homomorphism axiom being satisfied, which you need to make the change of variables of bijection. Right, so you'd first arrive the usual kind of sort of 3 redundant coherence axioms that follow from the triangle equation with McLean's pentagon. So you get these 2 and this one. Right, then you can show that this alpha H is a homomorphism, which means it satisfies these axioms. And that this will give you essential surjectivity. And then you need to check that the modifications are also homomorphisms in some sense. And by that I mean, where is it? So if you replace the alpha here with say a modification, then you end up with some axiom that sort of says that a modification is a homomorphism. But in that case, you end up with the pasting diagram instead of this square. Right, so that's what these axioms are saying. So the modifications sort of xi1, xi2, and this capital Xi should all be homomorphisms in some sense. And this will give you the fully faithfulness part of the equivalence. Right, so as for future work, right, so Marmolejo gave the definition of, say, distributive laws in terms of extension operators. Actually, until now, it hasn't really been possible to do this for pseudo-distributive laws, because if you use the usual coherence axiom, you just end up with a huge mess trying to understand what's going on here. But actually, now this should be like fairly straightforward to do if you use this minimal definition of a pseudo-distributive law. Right, and somehow these minimal definitions, they're a bit like the definitions in terms of extension operators, but where the operators are applied to identities. So it's like a base case of that, if you like. And I'd also like to find the analogous result of this for the mixed pseudo-distributive laws case. And that appears to be a bit more complicated. And this also showed up in some papers of Marmolejo, where he defines mixed distributive laws as well in terms of extension operators, and that one turned out to be a bit more complicated. And I also want to understand how this ties in with the KZ case, where if you reduce the axioms in the KZ case using the mates correspondence, then you end up with a sort of different minimal set of axioms. And I don't fully understand what's going on there, because the axioms that are redundant here using this approach end up being axioms you use in the KZ case, in the minimal definition. Right, so I'll just give you the references. And thank you.
All right, let's thank Charles for that. The usual silent round of applause. And if anyone has any questions, feel free to unmute yourself and go ahead and ask one. Maybe I can ask one question then. So the definition of a pseudo-distributive law of Marmolejo and the others,
yeah,
finally had 8 axioms, right?
Yeah.
And I'm slightly confused. Are you sure? Did you show that you can just delete 3 of those axioms?
Well, I showed that they're redundant because of Kelly's result about McLean's pentagon and the triangle axiom implying 3 others.
Okay, so 3 of them literally are redundant.
Yes.
You cross them off the list.
Yeah.
Okay, good. I just wasn't sure if you had shown that you could take these 8 and replace them by a different 5 or by a subset of those 5 or of those 8.
Yeah, I mean, this is just 3 of them were deleted. Yeah.
Good. So you did delete. That's good.
I have a question, if I may.
Yeah.
Yeah, speaking about these axioms, so correct me if I'm wrong, like I want to know if I understood it properly. These 5 axioms that you have then,
yeah,
are they like 4 of them should be, I'm guessing, the ones that make one a pseudomonad morphism, another one a pseudomonad opmorphism.
that's correct.
And then the 5th one, what should represent that one?
Right. I mean, the 5th one is just this interchange axiom between the 2 pentagons. Yes, this axiom that says this is pasting is equal to this one. Yeah. Yeah, and that's sort of the worst axiom, but it's the one that you need. Yeah.
Okay. Thank you.
Any other questions?
I have a quick question.
Yeah.
Is there, do you see this being useful as well to define like n-ary distributive laws for pseudomonads? Do you think that will be more accessible with these simpler axioms?
I think probably, but I haven't really thought about that much because it already gets quite complicated just in the two-ary case. I mean, yeah, probably.
Yeah, maybe. I mean, that's. I'm curious what the general advantage of working with the decagon type approach is, or what you think of it. That's extremely vague question. Or what's the advantage of this sort of approach compared to the classical one?
Right. I mean, the point is that you're reducing the amount of data needed to define a pseudo-distributive law, right? Because you have 3 modifications, not 4. And then the coherence conditions collapse because of that. Yeah.
So it should be easier to verify that you have a pseudo-distributive law in practice with these axioms.
Yeah. Yeah, I really use the sort of minimal definitions for that sort of thing, but yeah.
Uh-huh. Okay, any further questions? Well, if not, then let's thank Charles again for a nice talk. And so that's it for today. So next week we have Mike Lieberman. So see you then.